to this series on A Level Maths. We're going to get right into two more proofs. The first one is going to be proving that the expression n cubed plus 7 has a difference of 1 from a multiple of 7 for integers n where n is greater than equal to 1 and less than or equal to 4. So this calls for a proof by exhaustion, and that means we just cover all the cases. In this case, each case is just the different values n can take, but sometimes it might be saying, oh, n could be even or odd, and what can we consider then? Or n can be a multiple of 3, one less than a multiple of 3, and one more than a multiple of 3, and see what happens. But for this example, we're just going to plug in each number. So when n is equal to 1, our expression is 1 cubed plus 7, and that's equal to 8, which is 1 more than a multiple of 7. When n is equal to 2, our expression is 2 cubed plus 7, that's equal to 15, which is 1 more than 14, a multiple of 7. When n is equal to 3, we get 3 cubed plus 7, it's equal to 34, that's 1 less than a multiple of 7, 35. And when n is equal to 4, we got 4 cubed plus 7, and that is equal to 71, which is 1 more than 70, a multiple of 7. So that's our proof. Like always, we'd write some sort of qualifying statement, but that's about it. Right, now on to a proof by contradiction. So for about this little dot, we are going to do, well, a pretty classic proof. The proof on the specification is root 2 is equal to a over b, but I think I've done that twice on here before, so we'll look at instead root 3, and we want to prove root 3 is irrational. So I've already started here. What we're doing is we're assuming that it is rational. If it's rational, then root 3 is equal to a over b, where the greatest common divisor of a and b is equal to 1. That's the definition of a rational number. Okay. So working with that definition, we can square both sides and multiply it by b squared, and we get 3b squared is equal to a squared. Well, that means that 3 divides a squared, meaning that a squared divided by 3 is an integer, but that also means that 3 divides a. Okay, so if 3 divides a, then we can write a is equal to 3k, where k is some integer, and then we can substitute that into here, so we get 3b squared is equal to 3k all squared. Right, all we've done is substitute a equal 3k, and rearranging this leads to b squared is equal to 3k squared. Okay, expanding this and then divided by 3, and then by the same logic we used earlier, 3 divides b squared, meaning 3 divides b. Well, now we know that 3 divides b and 3 divides a, so that means the greatest common divisor of a and b is greater than or equal to 3, right? Because they both divide 3, so it's a divisor of both, so it's a common divisor. So the common divisor is even that, or a number bigger than that, and that is greater than 1, which was our initial assumption. So this contradicts our initial assumption. We've basically shown that by assuming root 3 is rational, it doesn't work, it doesn't make sense, right? We've contradicted ourselves, and therefore we say root 3 must be irrational. Okay, because assuming that it is rational leads to a contradiction, meaning it can't be rational, and what's not rational, irrational. Okay, there's a few subtleties with this proof, and you'll look into it yourself, but this is just an example of how to use that proof. Yeah, you have to be careful, and you have to give a little bit more of a quantifying statement at the end here, just sort of explaining your logic about the contradiction. So pretty much everything I said you have to write down, but this is the logic. Hopefully that makes sense. If you have any questions, let me know below. If you did enjoy this video, please be sure to like and subscribe, and I hope to see you in the next one.